Thank you very much, Gary, for that kind introduction, and it's, of course, a pleasure to be here for the Nozik Lecture. Actually, the 5 years ago, the reason why my career apparently did this was Gary was nice enough to nominate me for the RSC Chemical Dynamics Award, which was fantastic. So I appreciate that, and I appreciate the introduction. So we're here at the Nozik Lecture, and I'm going to talk about some of the work that we've been doing. But I do want to say, Art, of course, we've been working together for many, many years, for I guess 21 years. And I'll show you. Actually, we started before I came. So it's a little bit longer, but anyway, so science is kind of like a little family in some sense. It's a small community, we know. So I used to tell my wife and son, who are here, that so I mean it's local. I mean Seth had to pay all that money to fly me out here, and
by the way. We don't usually do this, but for Matt, we paid for first class.
It's first class. I got it.
So much we think of it.
And then even brought my family out. It was great. Anyways, I tell her that I'm famous all over the world, but only by about 5 people. But they're all over the world. But anyway, so science is a small community and a family, and we have scientific parents. So this is the academic family tree. You can actually look this up. You can look up what your academic tree is, and here's me. And I have 2 parents, Charlie Schmuttenmaer from Yale and Art Nozik, of course. And I'm just very, very grateful for what Art has done for me. So. All right. So just a little bit about, myself, and of course, my history with Art here. So I did start here at postdoc at NIST, but luckily Art he was kind enough to bring me on when this didn't work out quite so well. And this is now 2003. Now, this is what I wanted to show. Look at this. And I tell people don't believe this. I used to park right here in front of the surf, and it was a bad thing in those days if you had to park at the back of the parking lot. That means you got in late, right? You wanted to be right at the front because it was too far to walk if you're back here. I mean that's terrible. I mean, especially if it was cold. Bad. But anyways, I can imagine the picture that was here when Art started. There's probably nothing here, right? So anyways, I started here in 2003. We were doing new concepts for solar energy conversion, non-contact probes, the carrier dynamics, and so forth. All right, so at NREL, now this is what it looks like. You can't even see that parking lot. And now we have to park way over here. It's terrible. Now I have to I have to use my counter on my phone, so I know how many steps it takes. But anyways, and it's cold too. Walk all the way here. And anyways, when they were building this building, which now blocks that, I remember the director at the time basically said, "Oh, this is the house that Art built," and because Art did so much for NREL, I think the reason why this has grown so amazingly is partly because of people like Art. And there's a new building here. You can't see it, but if you go now, there's a huge crane. And so the future of NREL is I think pretty good. And going forward. All right, so yeah, my career, started with Art, became senior scientist and associate director, and then director, and so forth. So that's where we are. Okay, so this is the first paper when I was in grad school, published with Art Nozik. He actually came to NREL when I was my last year of Ph.D. and he gave a talk, and I was blown away. I didn't even know there was a thing called NREL at the time. Wow, this is really fantastic, and the work that he was doing was so inspirational. And so he talked to us, and I guess he liked what we were doing, and said, "Oh, we got this experiment to do." electronic coupling and indium phosphide nanoparticle arrays. So we did that. We were looking at, Art and Olga actually had published a paper year before showing some effects on the optical spectra when they made these nanocrystals closer and closer together. And so we did this experiment where we did this time resolved Terra spectroscopy, and you could see when they get closer, you get a big signal because the carriers start to delocalize over many nanocrystals and so forth. So that was great. I started us off here. I didn't want to. Oh yeah, I didn't say that. Anyways, 2003 it's published, although we started it a few years earlier. So, and this was, I was going to say, the volume 3 of Nanoletters. So I do have a paper. It was in volume 2, but you're going to get, or it probably has one from volume 1. But anyways, okay. All right, there's kind of 3 research areas that I've worked at NREL. And this one, semiconductor nanocrystals for improving. Still working on this. This is what I was working on with our semiconductor surfaces, and then these metal halide perovskites. That's what I'll be talking about. But I do want to talk a little bit about the first one and just let you know, a very important problem, important challenge, and we're definitely trying to push forward in this area. It's a scientific challenge, and that is, you can buy these really fantastic solar cells. They're great. I have some on my roof. They're only, 22% efficient is what I have on my roof. So that's still throwing away 80% of the available solar energy. So it's a challenge. How can we overcome this and get above that? In fact, I looked up. There's this article published in Science. This is the 125 challenging science problems, and this is one of them. What's the ultimate efficiency of PV cells? Can we break through this barrier? And so this paper was published a little bit later. So yeah, we can do this. This is Art Nozik. He worked on these concepts of how you can better utilize the solar energy spectrum. Concepts like MEG over here, intermediate band, up conversion, hot carrier solar cell. So I call this the Ross-Nozick limit, 67%. And then there's these other concepts. And we're working on nanocrystals for MEG and perovskites for hot carriers. But very interestingly, you can also do perovskites for tandems, and you can do this very cheap. And I'll show you, it's actually really impressive results recently. But we're still working on this. Paper just accepted in PRL, just found out on Friday. And the new concept, so the standard MEG concept is this. You have a high energy photon, generates a hot carrier, that hot carrier relaxes, excites an electron across the band gap, so better utilizing the available energy. So the new concept utilizes the same thing, but you can get this at a much lower energy by using a defect state here. So you can have this high energy photon, generates hot carrier, it relaxes by exciting a carrier out of the defect level. Now you might say, okay, for solar energy, that means the quasi-Fermi levels would be really small. So the way to sort of come about this then is to kind of marry the concept of carrier multiplication, MEG, with intermediate bands. So you have your low energy photons that can repopulate this state. All right, so that's kind of where that's going. So this is, of course, the efficiency for solar cells, and here's the single junction solar limit. So this is what I did want to say. Got a bad angle here. Can't see what I'm trying to say. But anyways, oh yeah. So here's a silicon over here. So that's the efficiency for silicon. Here's perovskites over here, and these are perovskite tandems. Anyways, all these technologies have this single junction limiting efficiency. This one down here, quantum dot, so it has a higher limiting efficiency. So I say, oh, we need to get rid of all this perovskite stuff so we can get back to working on quantum dots. But here, this one right here, this is perovskite silicon tandem. It's already over the single junction limit. Pretty impressive. And that's the one that apparently maybe is going to market soon. Okay, the MEG limit efficiency is way up here. So if we can keep working on this one, this is the quantum dot one. we can get up higher limiting efficiency. You might say, what are all these other ones up here? This because they're multi-junction cells and they're concentrators. So that's the 3-junction limit. This one up here is a 4-junction, 665 solar concentrated, and that gets 47.6. Really impressive. NREL has one that's 6-junction over here. Non-concentrated drops down to this one. Okay. Enough about that. Now we're going to talk about chirality. Okay, what's interesting about chirality? So I know I get this. Okay, I'm at NREL. Why are you working on chirality? How does that impact solar energy conversion? Maybe I'll explain it. I don't know. We'll see. What's interesting about chirality? Well, first off, what's chirality? So chiral is, sort of the Latin word for hand. So chirality translated is handedness, or your two hands are chiral. This one breaks the symmetry with a ring. Right. So they're mirror symmetry. They're mirror images of each other, and they're non-superimposable. Right. So that's chiral. So chiral structures are all over the place in nature. So this is some animal with really cool horns, and they're mirror images of each other. Quite impressive. In biological systems or plants or so forth, you get these little spirals. This one is somehow spiraling to the right and then switch to the left. This structure is also really cool, kind of some sort of spiral structure. You see these in shells, even in galaxies. They're spiral, and in molecules. These are chiral, and of course molecules of life. This DNA, they're spiral. So there's something very interesting and interesting about chiral structures and breaking that symmetry. All right, so this is paper I like to show. It's written by this guy Lawarence Award in the UK, and he says, okay, chirality is a central and unifying theme in modern science, links the properties of the universe and its constituent elementary particles, frozen in time of the Big Bang through organic stereochemistry to the structure and behavior of molecules of life, with much else besides nonlinear optics, nanotechnology, materials, electrical engineering, pharmaceuticals, and so on and so forth. So a lot of really cool stuff. All right, so this also I like to point out is sort of the value of basic science. So this is Louis Pasteur. So Jean Baptiste Biot, I guess, discovered optical activity in 1812, and his grad student was Louis Pasteur. And he found in 1848, so 30 some odd years later, an interesting phenomenon. So these guys knew about optical activity. That means like when you put linear polarized light through crystal, quartz, or sodium tartrate, it would rotate the point of polarization to the right or to the left. And so Pasteur, these guys knew actually in this 30 years that sometimes they would make the sodium tartrate, sometimes it would go to the right, sometimes to the left, sometimes not at all. They thought that was a completely different molecule, paratartrate, I guess. And so Louis Pasteur, he crystallized this paratartrate, and he found these two different types of crystals. So that's a good picture of them. But this is quartz. It's also chiral. And then you can see these are mirror images of each other, but I can imagine if you're growing little crystals of this, it'd be really hard to pick them apart. This is what tartrate crystals look like. So I can imagine it was a painstaking process. And actually, there's a museum you can go and look up. These are the actual crystals that Pasteur used. So he separated them out, and then he found out that, okay, if you redissolve this one, or if you pass light through this one, it went to the right. If you went to this one, it went to the left. If you mix them together, then there was no rotation. So from that, he deduced that these molecules were chiral. And it wasn't until even many years later, 1874, that people found out about this tetrahedral asymmetric carbon. So that's kind of what it looks like. These molecules are what makes up these crystals. and they're chiral. So he, of course, linked chemical structure to optical activity, discovered there's enantiomeric pairs, and that led to, you know, all this great work in biomolecules and medicine and so forth. In fact, in 1857, he was working on fermentation, and he found that if he had some unidentified microorganisms with the plus version of tartaric acid, it was consumed, and with the minus, it wasn't. So from that, he was able to deduce that most biomolecules are homochiral. So amino acids are left-handed and sugars right-handed, and our DNA are homochiral. And so that's also one of the unanswered questions. What is the origin of homochirality in nature? Nobody knows this reason. Lots of ideas, but still an unknown question. Here's another one that I'll talk about a little bit later. But is it possible to create magnetic semiconductors that work at room temperature? And turns out it's related to chirality. So, all right. Michael Faraday, he was also working on this. He discovered magnetic field can induce optical activity in 1845, called the Faraday effect. All right, so this was a key demonstration that connected magnetic and optical phenomena. So Faraday noted in his diary, there was an effect produced on the polarized ray, and thus magnetic force and light were proved to have relationship to each other. This fact will most likely prove exceedingly fertile and of great value. Well, that's an understatement, I guess, because, you know, in 1870s, after this, you know, Maxwell's equations came out describing, you know, everything that we know about light and magnetism. All right, so this is light interacting with a chiral material. So if you have a linear polarized light, you can think of this as either left or right, you know, polarized light, equal amounts. And when it passes through a chiral medium, it will absorb one of those polarizations more than the other and turn this linearly polarized light into elliptical polarization. So that's usually reported, CD spectra is usually reported as a degree of ellipticity. And so that's how much this linear polarized light gets turned into elliptical light. The Faraday rotation is the same kind of idea, except for you're not absorbing. It's the refractive index part. You have a rotation of the light. Linear polarized light goes through some medium and it rotates polarization. So, you know, the circular dichroism is connected to these light matter interactions, molecular structure, environment, dynamics, and so forth. In fact, I was at Yale not too long ago for this other lecture, and I ran into an old professor of mine, Pat Piccaro, and he told me about this study that they did. They were looking at the optical activity of this molecule. Very rigid molecule. It's not very polar, polarizable. And what they found is, you know, they can dissolve in all these different solvents, and they get different optical rotation of the same molecule dissolved in all of these different solvents. You can almost get any value you want over here. So it's like, well, what is controlling optical activity? If you do high-level DFT simulations, you get this red curve that doesn't follow any of the things that are measured. Pretty interesting. And if they do, so Pat, you know, his thing was they wanted to do in gas phase, so he came up with this really clever way of measuring optical rotation of gas phase molecules. And so they can only measure it in two wavelengths here and here. And it doesn't really match anything. And the interesting thing, I guess this green line is the one that gets it the closest, and that is acetonitrile. So solvent you would not even think would be the one that gets closest to the gas phase. But anyway, so I just pointed this out because it's pretty interesting. Like, you know, well, no, so this work from Azim over here. So he published a paper just recently in Nature Chemistry where, okay, he's taking achiral perovskites and adding these chiral additives and measuring the circular dichroism. And really fascinating. As he adds more and more of this molecule, it actually goes up positive and then goes negative, which is very same chiral molecule, adding it into this this system. And then it goes up super linear. So this is chiral amplification. So you get both CD inversion and amplification things. So he's here. So if you have questions about that, you can ask him. All right. So chirality, this kind of interesting. It's a merging area in physics and chemistry. And of course, I just showed you that it's been known for 100 years, 200 years. And people know about chiral molecules and so forth. So why is it an emerging area? Well, because, okay, chemists and physicists don't talk to each other, I guess. Physicists, they also know about chirality, but it's kind of different. They talk about leptons, chiral symmetry breaking, and electromagnetic weak force. It turns out electromagnetic weak force, when you break parity, these two chiral molecules have different energies. They're very small, we hard to measure, but they're different. There's topological effects, DMI interactions, spiral galaxies, and so forth. And so the kind of merging area is the intersection between chemistry and physics. So, you know, I'm a physical chemist, so that's where we live. So anyways, possible mechanisms: chiral induced spin selectivity, spin momentum, and orbital momentum locking, chiral induction, magnetic exchange interactions, chiral phonons, and so forth. And all sorts of different kinds of applications people are thinking about: pharmaceuticals, discrimination, sensing and security, quantum cryptography, quantum computing, spin qubits, different kinds of displays, holography, and spintronics and magnetization and so forth. So it comes down to this phenomena that I want to talk about. It's chiral induced spin selectivity. And the idea here is if you have a chiral molecule, this was sort of discovered by these guys, Dave Waldeck and Ron Naumann. So if you have some chiral molecule and you pass electrons through it, you will somehow at the end of the molecules have only one of the orientation of the spin. So the electrons have two spin orientations, and only one makes it through. And then if you switch the chirality but keep the current direction the same, you get the other spin configuration. Okay, so that's pretty interesting. You can kind of think about it like this: if the electron is traveling in this helical path here, it experiences a spin orbit coupling and sort of splits the energy levels of the spin, and then it depends on the chirality and the direction of the current flow. All right, so just to remind you, moving electrons are also chiral. So if you have, say, an electron with a spin and it's just sitting there, and it's not sitting there, not chiral. But as soon as it starts to move, say if you have some spin direction like this, and you have some momentum in this direction, this traces out a helical path. And if you keep the direction the same but reverse the spin orientation, then you have the opposite helicity. So, you know, chiral objects behave the same when their interaction is the same, but they interact differently when they're RNS. And so you can kind of think about this in that way as well. So as I mentioned, it's been measured many times. This is Ron Naumann and David Waldeck, and they were basically, okay, taking gold or something with oriented chiral molecules and then passing electrons through them. And then depending on the chirality of the molecule here, they would get preferential transmission of up or down spins. So it's been studied for a range of systems, mostly employ this magnetic conductive probe AFM measurement, which I'll mention in a minute. But there's now all kinds of measurements of this. This is sort of the spin polarization that you get at the end of the chiral molecule. So you have molecular organic frameworks, metal halide semiconductors up here, DNA, peptides, polymers, and so forth. But I do want to say there currently is no general model that can explain all of the observed effects ascribed to CIS. So it's a really interesting area of science, and it's still being understood and explored, and that's okay. Because you know, as I mentioned, we still don't know why we have homochiral molecules either. It's okay. All right, so this, if you want to read all about this, there's a chemical reviews paper from these guys here. published this year. And you can see there's huge interest and in 2019, we demonstrated that this chiral-induced spin selectivity is also in chiral perovskites. And I'll explain, in a little bit why this I think is important and different from what's been done in the past. All right, so chirality, we kind of introduce it in two ways. It's morphological. You can take an achiral system and kind of grow it in the presence of chiral directing agents, and then you get some sort of twist here, or you get some sort of distortion of your nanocrystals, or what have you. Or you can crystallize your achiral building blocks with chiral molecules, and they're embedded in there, and then they sort of once now you have a crystal structure, it's got chiral objects in it, has to crystallize in the chiral arrangement. And that's what we've been studying on, but we also doing this morphological stuff as well. So this is kind of the perovskite systems, Matt Hosinger over here. So you take your three-dimensional perovskite system, you add this chiral amine, and you end up with this layered system. So you have layers of metal halide octahedra interspersed with these chiral molecules. And it has this space group B21, 21, 21. So this is sort of the prototypical chiral perovskite that we've been studying. There are, of course, examples of inorganic chiral systems. I mentioned quartz, for example, is chiral. But to control the enantiomer, the handedness is a huge barrier. You don't want to have to crystallize these things and then kind of try to figure out which ones are right and left. But that's kind of what you do. Tellurium is the sort of prototypical example. It's chiral metal, or it's chiral semiconductor. But when you grow it, you don't know whether you get this version or that version. And the way some people try to figure this out is they etch the surface, and if they get this etch pattern, it means it's right or whatever, and this one it's left. And so then they can study their properties. But to actually separate is quite hard. But I should note there's a huge research effort in trying to grow tellurium with only one-handedness. So probably there'll be progress on that. Okay, pure organic systems, you can control the enantiomeric purity because the organic industry has put a lot of effort into making, homochiral molecules for, lots of different reasons, but the drug industry, for example, because again, our molecules of the body are all chiral, so if we're going to have a drug, it has to be the right enantiomer. But it's, you're not going to put these organic systems into an electronic platform unless you grow chiral polymers. All right, so these hybrid systems allow you to marry these two things. You can take the chirality, the homochirality of the organic compound, and you can couple that with the semiconducting properties of these metal halide perovskites. And that's what we're doing, and then we're trying to understand how to incorporate them into devices. So this is showing one of these structures here, and there's three kind of important things about these chiral perovskites that are really important, I think. One is the chiral molecules are oriented out of plane. So here's your system over here. The chiral or the inorganic planes are parallel to the substrate. And these organic molecules are oriented. So everything's oriented. You have a nice oriented system. Chiral perovskites are highly textured and crystalline. So when you make thin films of them, you still get this highly textured system where the planes all arrange themselves parallel to the substrate. And you can get these smooth, thin films and via spin coating. And so that's what's shown over here. You get nice, smooth, thin films that you can incorporate them into electronic applications. And of course, you also get chiral transfer. So this is the inorganic electronic transitions over here. And you can see they all have optical activity. And so this mechanism of how the organic chirality somehow induces a chiral response in the inorganic is also a very interesting topic. And I was just at the MRI, so there's a whole session on discussing exactly this phenomenon and trying to understand exactly how that happens and under what circumstances and what this spectrum means and all that. So very interesting. All right, so this is the experiment. It's a magnetic conductive probe AFM. You have an AFM tip that's magnetized, and then you measure current through it. And what Peng noticed here was that when he did this with the achiral version, it doesn't matter whether your tip is magnetized up or down, you get the same IV characteristics. But when you make this, say, right, and you have, say, your tip magnetized up, then you have this low resistance state, high conductance. And if you have your tip magnetized down, keep the chirality the same, you have high resistance state. So you have two states. Interesting. And then if you, so what does that mean? That means, okay, if you're going to magnetize the tip, you have these at the Fermi level, you inject your spins up and you block the other spins. And then when you change to the S version of the perovskite, you get the opposite behavior, right? Now, when the tip is magnetized down, you get good conductance, and if the tip is up, you get pulled. So that means now the other spin can get through the system. So now what that means, of course, is we can have a way of preparing spin polarized electrons. And you can say, okay, what's the polarization efficiency? And it's pretty good here. It's defined in this particular way. Okay, so what? Show we can do that. What does that matter? So we do have this EFRC we talked about, and the EFRC's goal, the mission here, is to demonstrate it unprecedented control over spin, charge, and light through synthesis and characterization of these systems. And we have this whole structure to do this. All right, so this is a charge to spin interconversion process. So how can we use this chirality to control spin, charge, and light? So there's a couple of ways. There's a phenomenon we can do cis-enabled spin valves. So this spin valve it was sort of awarded this Nobel Prize, and it sort of makes up all of magnetic memories, but it's based on two ferromagnets. So if you have this ferromagnet, you have a low resistance state and a high resistance state, depending on the polarization of these two ferromagnets. So that's the idea. But with cis, we can take one ferromagnet away. We can make also a spin valve. We have a low resistance state, high resistance state, and it depends on the chirality. So we published this paper. You can say, oh, well, your magnetic resistance is only 0.2%, but Azim here, he's done really good. And so now he can get this up to over 100%. But really impressive results. Yet published. Okay, what else can you do? You can do a CPL photodetector, and so you can make this with Jeff Blackburn. You can make some sort of detector over here, make it chiral, absorbs light, absorbs left-handed or right-handed. It'll have a higher response depending on the chirality. So you can detect whether your light source is polarized. So that's a CPL light detector. There's other demonstrations. You can have something called spin-dependent photogalvanic effect. So you can just drive current with light, with no other kind of bias. You can just shine light on it. If it's circularly polarized light, it will drive current to the right. If it's the other polarization, it'll drive current to the left. You can also use phonons. This is work from NC State, Dali Sun, it's in our center. But anyways, if you induce a temperature gradient across this chiral film, you can drive a chiral phonon into a proximal metal here, and you convert the spin into into polarized, or this phonon into polarized spin. Okay, you can do magnon coupling as well. These are in magnetic materials. All right, you can do a spin LED. That's a reporter of this. So that's kind of, okay, we're going to convert charge to spin, and now we're going to convert spin to light. And we use metal halide perovskites that are achiral for that. And just to show you, here's the band structure of this guy over here at the band edge. And so you can kind of think about this as just this two-level system down at the band edge, because the spin over coupling pushes the other p states way high, whatnot. You have J 1/2, S at 1/2 over here. And so what that means is you have these M sub J levels. And so if you shine circularly polarized light on this, this system, you can drive this transition. And that means you can optically generate spin polarized carriers with circularly polarized light. And since you can do that, you can do the reverse. If I inject circularly polarized carriers and it emits, it'll be polarized emission. So that's what we did in this paper here. So you inject spin polarized holes through this contact into this emitter layer, unpolarized electrons through this electrode. These electrons have to find the right hole to recombine at this interface, and they emit circularly polarized light. In this case, we only got 3% circular polarization. But the really sort of novel thing about this paper is that this is all done at room temperature. We are showing that we can get spin accumulation in this non-chiral emitter layer without any magnetic fields at room temperature and no magnetic components. So that's impressive. So chiral perovskites can also transform traditional optoelectronics. All right, so this is a major goal, actually, this paper 2012 over here. So yeah, people know, okay, I showed you the magnetoresistance effect. Those are with ferromagnets and metals, and you can control spin in that kind of system. And we all know semiconductors do all sorts of great things. So of course, people want to marry these two and control spin, charge, and light, right? That's what we want to do. But there's a huge barrier to this, and it happens. This ferromagnetic semiconductor interface scatters the spin. So there's this well-known conductivity mismatch. You have a metal next to a semiconductor, try to inject spins across that interface, and it doesn't quite work. And so, of course, this is what people are trying to do with these kinds of things. They put this tunnel junction in here. It has to be highly crystalline and so forth. This is quite an art, but it's great. It works. Okay, so we can do this in very solution deposited systems. We have our chiral perovskite, we have a non-chiral perovskite as well. We can measure the spin across this interface, and we also get really high spin polarization across the interface. So that means already that our spin injection over here is already really good. And that's because it's a semiconductor junction, not a semiconductor metal junction. And so you don't have this connectivity mismatch problem. All right. So what Matt said is, can we just implement this in we already have, laying around optoelectronics based on 3-5 semiconductors and so forth. And so can we just incorporate chiral perovskites into, the structure and transform that into one that can also control spin? So that's what he wanted to do. And Kirsten Albury, who was at NREL, was just working on this project of making this LED with 3-5s. It's based on a multi-quantum well structure. So she had a lot of these samples laying around, and I said, oh, I'm going to see if I can put my chiral perovskite on, see what happens. And so he did. I'm saying this very glib, but it took him a year. A lot of good work here to figure out how to do this, and it works. These things with the chiral perovskites emit, and of course you get polarized emission. This is the R version. So here, the green trace is always above the red trace, and here the red trace is always above the green trace for the other chirality, and that's the different polarizations. And so you can get a degree of polarization of over 15%. So that's good. It's already improved the spin polarization out of this device 3% up to 15%. All right, so of course, what we're showing here and what's important for this kind of thing is yeah, we can get spin injection across this chiral semiconductor interface, and we get spin accumulation in the emitter layer that's not chiral. Okay, so that's what we're getting at room temperature with no ferromagnetic components. And there's another caveat here, and that is the spin orientation is out of plane, not in plane. So we normally get ferromagnet, but this gets out of plane. So there's a lot of advantages for that, for all sorts of different potential applications, but for this one, it has some benefit for the direction that light's being emitted in the polarization. Okay, can we do the opposite? It's my last topic here. Can we convert spin to charge can we convert spin to charge and light? So now we're going to do the different. We're going to do the opposite thing. Instead of converting charge to spin and light, we're going to convert spin to charge and light. All right, and the work that EFON is doing over here. So cis is charge to spin conversion process. Inverse cis is spin to charge conversion process. All right. So to do this, we have to generate spin accumulation at the surface of the chiral system, and then we have to be able to measure the charge current that maybe is induced. So we're going to use terahertz spintronics field. So the basic idea is this. This is let's say a ferromagnet. You have a femtosecond laser pulse that hits the femtosecond or hits the ferromagnet. It heats it up. You have a spin Seebeck effect. It drives spin current in this direction over here, and then you inject that spin into, say, a proximal heavy metal, undergoes the inverse spin Hall effect, and generates a spin current that's perpendicular to the generates a charge current that's perpendicular to the spin current. And then you read that out, since this is ultra fast, you read that out using terahertz spectroscopy. And terahertz spectroscopy is very powerful in this way because you're reading out this pulse. Anytime you have moving charge, you have accelerating charge that will radiate a field, like an antenna. If you have something that's moving like this, it'll radiate out, and that's all you're doing. And terahertz, since you're measuring this in the amplitude level, you can get the amplitude. So if the spin orientation is, say, in this direction, then you get charge current going in this direction. That's up. If it's in the other direction, the majority spin is in the other direction, then you'll get charge going down, and that's this blue one. So you can tell the direction of charge with this kind of technique. So this work from EFON. So instead of using a ferromagnet, or excuse me, instead of using a metal, we're going to use a chiral perovskite. So ferromagnet over here in contact with the chiral perovskite. And now we're going to have the spin orientation out of plane and use a femtosecond laser pulse, generate this charge current, spin current that gets injected into the chiral perovskite, and then measure the charge current that's induced. So importantly, as I mentioned, terahertz spectroscopy can both get the polarization, that is the direction of that charge current that's generated, as well as the polarization, right? Or excuse me, as well as the polarity. So I can tell if it's going forward or backwards, and we can tell which direction it's going in. All right, pretty cool. So what EFON did here, the spin is oriented in the plane. She shines this guy in, you get a spin current injected with its orientation in the plane, and she's going to measure charge current being generated in perpendicular direction, EY direction. And there, that's what you see. And she changes the polarity, then nothing changes. It stays the same, but you have this ultra fast current being generated. And that's because this is due to the inverse Rashba-Edelstein effect. So you have spin splitting in your bands in these systems. And if you inject spin polarized carriers along the X direction into, say, one of these bands in the K direction, it picks up some velocity in the Y direction. And if you reverse the spin, then it goes in the other direction. It's not dependent on the chirality. It's only dependent on the distortion, in-plane distortion. Okay, so, but in this same experiment, you find very clever. She said, okay, I'm going to look in the X direction, not just the Y direction, but the X direction. And in the X direction, there's a field also generated, a current also generated, sorry, and it does depend on the chirality. And that's because you have an in-plane chiral axis. And so you have this inverse cis in the plane. You get charge generated in the plane as well as perpendicular to it. So very nice. Okay, and that's this chiral spin orbit coupling on the X direction. Okay, so to measure the out of plane, we have to tilt the sample a little bit so we can measure this, because remember that if you're looking at an antenna is going like this. You look over here, can't look directly down the antenna's axis, so you have to turn it a little bit, and then you can measure X and Y. Okay. So, okay, one chirality, one polarization, the spin goes up, or the charge current goes up, and then you change the chirality, but keep the, keep the polarization the same, chain goes down. You can also change the magnetic field and you get reversal of the charge current. Okay, so that's great. What does this mean for cis anyways? Again, now you have spin splitting in the chiral axis along the z direction. And so now when you put spin along the z axis, put it into the spin split band, it accelerates charge in that direction, and then that's what's measured out. So now if you think about what cis is doing, you're injecting a unpolarized carrier, charge carrier into the spin split band. It experiences an effective magnetic field that polarizes the electrons. All right, so that's what it is. It's a linear momentum velocity spin. Okay. Take home message, 2D layer perovskites are these chiral systems. They produce novel chiral semiconductor system. Chirality is introduced, provides new handle on controlling spin, charge, and light. Novel applications can transform traditional optoelectronics. Okay, what is the future? What's coming next? All right, so, well, future is uncertain, of course. But I was very interested. I went to the MRS this last week, and I went to this talk on terahertz spintronics, and there's this paper I published in grad school, 2003, on doing this. What we had is a ferromagnet. We came in with a laser pulse. It hits the ferromagnet, and you get the terahertz emission due to demagnetization, rapid demagnetization. All right, this was 20 years ago, and went to a talk at the MRS trying to explain the physics of this process. How does demagnetization happen so fast, right? And it's published in this paper in 2024. So anyways, theory has a lot to catch up to experiments. Okay, so chirality, chiral electrodes, we talked about this, photochemical reactions are dependent on spin. You have spin orientation out of plane, so that means when the molecule comes down, it can see the spin, it's not in plane, very important. You can have chiral, photocatalysis, so water splitting, CO2 reduction are all dependent on spin. You have spin orbit torque phenomena. This is a non-collinear spin orbit torque, if you will. So new kinds of physics here. Orbital torque, I didn't talk about that at all. Orbitronics, spintronics, optospintronics, spin LEDs, spin transistors, impact on quantum information, and of course, your imagination of what could be done with this. All right, it's a new method for controlling interconversion between spin, light, charge, phonons, magnons, whatever. All right, just collaborators. This is a plot that NREL makes now. So this is me over here, all these collaborators. And there's two big lines here. One is to Art Nozik, of course. We have over 50 papers published. It's fantastic time with Art. And Joey Luther over here. Joey was the second person I met at NREL. When I walked in the door, I knew Art, of course, met Art. And Joey was number two, so we know each other for many years. And I love working with Joey, he's a great guy. And of course, all these other people, Jeff Blackburn here, and I was up here, Azim, a lot of good people, Victor Klimov even there. Of course, these are the best people that are doing all this work, and so thankful for all of them. Hei Peng and Young Hyun are gone, started off. Azim and Yifan are doing a lot of the work I talked about today, and Matt Ozinger. And of course, I didn't talk about the work from Marissa or TK. TK is looking at breaking symmetry and slowing cooling down, charge carry cooling down in nanostructures and so forth. And Marissa's doing spin dynamics and really interesting structures. And Margareta, she's just getting started with looking at chiral interfaces and surfaces and so forth. And Jacob is the optics person who's doing just fantastic work. And I didn't have a picture of PS. I think he's here. Probably online. But anyways, he's a chiral guy. All right, that's it.